Welcome back. So in the last class, we discussed several heteronuclear interactions and we did even analyze a couple of heteronuclear spectra like fluorine spectra, carbon spectra, varieties of things. So I also gave you an idea about the coupling strength when heteronuclear involved, how to analyze the spectrum, varieties of information was given to you in the last class. Today, what I'm going to do is I'll continue these heteronuclear interactions, introduce some interesting things which you can come across in NMR, like how when heteronuclear is there, how it can affect your NMR spectrum called isotope shifts, isotopic effects on the NMR spectrum, and then we'll analyze a couple of spectra of different nuclei. With that, then we can go to a different topic. Okay. Now, one important thing we should know is the J coupling between equivalent spins. That is what we should know. For example, consider proton-proton 1J HH. That is, I said, it is in the molecule hydrogen. There are two protons joined by a single bond. Two hydrogen atoms joined by a single bond. Now, if I take the NMR spectrum of that, we'll get a single peak. Now, the question is, how do I get the J coupling information? Remember, I gave an example by doing satellite analysis. In the case where proton NMR will not give me the coupling information among equivalent spins. For example, in the cis and trans of disubstituted ethylenes and others we saw, symmetrically disubstituted, the protons are chemically equivalent and gave a single peak. However, we looked at the carbon-13 also. We included carbon-13 also into the molecule at the natural abundance. When that was brought into the picture, you broke the symmetry of the molecule. Automatically, symmetry gets broken. Instead of A2 spin system, it becomes A prime X spin system. As a consequence, we are going to get, if I have a single proton peak coming because of carbon 12 attached protons, there are satellites on either side comes because of carbon 13 isotope of the molecule. This we saw. Especially in the molecules which we discussed in the last class, where cis trans protons had chemical equivalence, whose coupling was not seen in the proton spectrum. We saw that in the satellites because it became A prime X and we could get AX coupling, A prime X coupling, everything. So we were able to get proton-proton coupling information from the satellite analysis. So homonuclear coupling, which is not reflected in the proton spectrum or one-dimensional proton spectrum, we could extract in one way. Now I am posing a question like this. This is a hydrogen molecule. Here, where is the question of carbon? I cannot break the symmetry like in the previous example by bringing carbon 13. Now both are proton. What do I do? I have to break the symmetry. I have to get the HH coupling. So one thing is, of course, to retain the molecule aspect, nature of the molecule. Best thing is, why can't you substitute proton, one of the protons, by a deuterium? Now, what is going to happen in the NMR spectrum? This HH coupling is not reflected in the spectrum, proton-proton coupling. But what about HD coupling? Remember, deuterium is spin 1 nucleus. This is spin half nucleus. Now I am observing proton. What will happen to the proton peak? Remember, we discussed in CDCl3. Spin half nuclei coupled to spin 1 nucleus. What is going to happen? Then this proton will be split into 3 states, 3 lines or 3 peaks of equal intensity 1:1:1 because deuterium is spin 1 has 3 energy states, -1, 0, +1. You understand? As a consequence, we are going to see 3 peaks in the proton spectrum because of HD coupling. Sure, we are going to get a 3 peak like that. 3 peaks. What do the separation of peaks gives me? If I measure the separation from this peak to this peak, any two adjacent peaks, if I take, I am going to get JHD, J coupling between proton and deuterium. So how does it solve my problem? Remember, in the carbon-13 satellites, when you are analyzing, you are directly getting JHH from the satellite analysis. But we analyze this and we get JHD. So how does it solve my problem? There is a formula, there is a way you can get. When the isotopic substitution is there in a molecule like this, when I know HD coupling, HD scalar coupling, because deuterium is the isotope of hydrogen, there is a simple formula. If I know the gyromagnetic ratio of this and gyromagnetic ratio of this, then I can get the J coupling between proton and proton if I know this. Or if I know this, I can get this. Very easy. Because that is given by a simple expression. 1JHH, because we are looking at 1JHH here, divided by 1JHD is equal to gamma HH over gamma HD. What is gamma HH? We know that 26.75 into 10 to the power of 7 radians per Tesla per second. That we should not forget. Remember, I told you also, the gamma of deuterium is 6.42 times smaller. And I was explaining to you the table of NMR active nuclei with their properties. In the first or second class or one of the classes, I discussed this and told you gamma of deuterium is 6.48, whatever it is. So in some books they 6.2, 4.4 to 4.84, it doesn't matter. You can get the approximate value and the exact value from the one of the good books. So this gamma of this one is different from proton by this amount. This is smaller by this amount. So according to this formula, if I know the ratio of JHH to that of JHD, this is proportional to or equal to gamma H over gamma HD. So what do I know here? I know JHH. I want to find JHH. I don't know JHH. I want to find JHH. I know this JHD. I measured from the spectrum. I know gamma of proton. I know gamma of deuterium, which is this many times smaller than gamma of proton. Simply plug in the values for gamma, plug in the value of measured JHD. What you are going to get is JHH. Very easy, right? In an equivalent spin system, you can do that. Of course, you can do the same thing in the previous molecule, what I showed you. Okay, 3-bond HH coupling in cis and trans substituted ethylenes. We saw that, in such cases also, you can do that. You can get HH coupling by making deuterium substitution. But there's one small difficulty there. What is the difficulty? Remember, 1-bond JHD itself is so small, of the order of 6.4 times, that's 6.45 times smaller than that of proton. If I go for 3-bond, maybe negligibly small, sometimes you may not be able to measure it also. This coupling may be hidden within the line sometimes, 3-bond or 4-bond HD coupling. You will not be able to see because of low gamma of these things, 6.45 times lower than that of proton. So that is why that was not a practical situation there. So what we did was we looked at the carbon-13 satellites. What we did is in the proton NMR we get satellites. They are called carbon-13 satellites because they are coupled to carbon-13. Of course, in the proton spectrum, satellites are called carbon-13 satellites because they are coming because of coupling to carbon-13. So we brought in carbon-13 in natural abundance for the molecule to break the symmetry. That was feasible in that molecule. But in this molecule, there is no carbon-13 at all. First thing, so we have to use a different method, and this is the procedure which is adapted. Changing the proton to deuterium and measuring the JHD coupling and obtaining JHH by using this formula. Okay. So now we will see how to get the J coupling between magnetically equivalent nucleus in a simple another example like this. This is CH2Cl2. What I can do is, of course, I can bring in carbon 13 here. Look for the carbon 13 NMR. What I am going to see, because it is coupled to two protons, carbon 13 has to be a triplet. What does that give me? JCH. But does it give me JHH? No, it does not give me JHH again. So in this case, I can't use carbon 13 also. Okay, I cannot even break the symmetry. How do I break the symmetry here? Because it is a, this is all the, even if I change it to deuterium, both of them or one of them, then you have to get 2 bond JD, 1 bond CH coupling you will get, and 1 bond CD coupling you will get, and 2 bond HD coupling you are going to get if you break the symmetry, and which will be much smaller, 2 bond HD coupling. So one of the possibilities in this case, into getting into instead of carbon 13, why can't I deuteriate one of them, one of the protons? You get, when I deuterate that, you get CHDCl2. This is another way. So I can see when I can see this CHDCl2, protons coupled to deuterium gives 3 lines of equal intensity. Okay, I got 3 lines of equal intensity. What did I get? JHD here. Simply plug in the values what I gave you. Now I got this. I'll get this value. And literally in this CH2Cl2 molecule, the real NMR spectrum, when it was recorded, you see 2 bond HD is very small, 1.1 hertz. Now if you want to go to 3 bond, how do you measure it? 3 bond HD. That's why in other molecules that was not practically feasible. So it is 1.1 hertz. Doesn't matter whether it's 1 bond coupling or 2 bond coupling, 3 bond coupling, but this formula is valid. Now plug it into this formula and you are going to get JHH of 7.1 hertz. Just plug it in these parameters. So we know in the systems where we have magnetical equivalence, we will be able to get HH coupling, which is invisible in the proton spectrum, by using either carbon 13 satellites or making isotopic substitution, and we see the HD coupling, and from that we can get HH coupling. This is all well known. Okay. Now let me take the example of this one. I took CH3CN. Of course, no problem at all. We get a single peak. But I want to get the J coupling in that. What do I do? There are 2-3 possibilities for me. I can think of various options. Can I use carbon 13 here? Why not? Okay, in the proton itself, look for the carbon 13 satellites. See whether you can break the symmetry. See whether you can measure the J coupling in the satellites. Or look for the carbon 13 spectrum, you get only CH coupling. Sometimes it is always advantageous to have isotopic substitution. Very simple sometimes. Look at this molecule. Instead of CH3CN, I made CHD2CN, or I can make CH2DCN. What did I do here? Remove one of the protons and put D here. In this case, remove 2 protons and put D2 here. Now we have 3 different isotopomers, 3 different molecules. Now take the proton spectrum of this, and this is a CH3CN single peak. It has to give a single peak. Now if I take CHDCN, how many peaks I expect? CHDCN, CH2DCN. So when it is coupled to, deuterium is coupled to proton, CH2DCN, doesn't matter whether it's CH3 or CH2 or H3, doesn't matter. It is coupled to single deuterium. So what will happen? We get 3 peaks of equal intensity, 1:1:1. Please remember, I said it is coupled to spin 1 nucleus. As a consequence, these 2 protons are split into 3 lanes of equal intensity due to spin 1 of deuterium. Fine. So you can get this, and this is C3CN. You can already see there is the isotopic shift because of substitution of a single deuterium. Next, alternatively, why can't I see this molecule? That's also possible, right? That also will couple to this one, and I can get HD coupling there also. Once I get HD coupling, I can convert to JHH using my formula. Do that. If I take the spectrum of that, it is I took the mixture of all the three are taken. Now look at it. You are going to get for when two deuteriums are coupled to proton. One of the examples you worked out, it is going to give a pentate with intensity pattern 1, 2, 3, 2, 1. I will remember I said this. I hope you remember in one of the classes, couple of classes before, or so I mentioned to you when spin-off nuclei is coupled to two equivalent spin-1 nuclei, you get a pentate of this intensity. 1:2, 2:3:1. There is a Pascal triangle also for this, you can work out. But in fact, I worked out by a family tree approach and showed you how you get 1, 2, 3 to 1 intensity. Doesn't matter. You remember, we have got it now. So where is the center of this? Center of this is here. When CH3CN is there, this is the chemical shift. When I substitute for one deuterium, this is the chemical shift. When I substitute with two deuterium, and this is the chemical shift. What is happening? Because of heavy atom, when it is substituted, because of isotopic substitution, there is a shift in the chemical shift position. This is what I said, isotopic effect. How much it shifts? For one deuterium, if it is this, two deuterium substitution, if it is this, if you have 3, 4 like that, it can linearly change like that only. You can easily find out shift because of isotopic substitution. Normally, it is expressed in parts per billion, or sometimes if it is large value, parts per billion. Okay. Now coming back to our J calculation, I can measure JHD here from the spectrum, either this one or this one, any of them you take, and that is the measured value is about 2.6 hertz, multiply with the gamma of deuterium, and the coupling what you get for CH3CN, proton-proton coupling is 16.74. Indirectly we got the JHH between the protons in CH3CN, although in the proton spectrum we get a single peak. This is a very important point. Now I'll discuss something about what is called isotope effects. Of course, just now we discussed isotopic effect. There is no point in going for this. CdCl3 is one thing. It gives 3 peaks. I explained already. And if you add another deuterium for that, I showed you. Just the slides were there, so I'm repeated. So I'm showing you. We get 1, 2, 3 to 1. And when I have a 2 deuterium and 3 deuterium, we get peak intensity 1, 3, 6, 7, 6, 3, 1. Okay. And then we also saw how much is the shift in the deuterium position. Isotopic shift because of deuterium. This was explained in the morning, so I didn't remove the slide possibly. So I'm repeating, I'm quickly going through. This is a triplet because of CH2Cl2. I'm looking at carbon 13. This is 1JCH. This is delta of carbon. Chemical shift. Now, this is when one deuterium is present. See what is happening is this will be a doublet because of CH, and one deuterium makes each of them into 3 lines of equal intensity. Each doublet line, each line of the doublet will become 3 lines of equal intensity. If you take the center of this, it is moved by this much. So this is the isotopic shift with the substitution of one deuterium. Now if I have 2 deuteriums, and this is what it is. 1, 2, 3 to 1, that's what we got. So now what is the chemical shift here? This one. You see, from here to here by a substitution of 2 deuterium. All this becomes because of isotopic substitution. Please remember, in many examples, the chemical shifts will shift when you make isotopic substitution. This is the important point which you must remember. Okay. Now, isotopic shift is 0.19 ppm per deuterium. One deuterium it is here. If I have 2 deuterium here, if there are 3 deuterium here, it keeps on changing. So what does it tell you? I also told in the morning, by the substitution of a heavy atom, the peak shifted to the high field. This is one of the concept in this case you should remember. Just by substitution, it shifted to the high field. Okay. Now I'll take another example of a very big, very good molecule. While explaining to you active and passive couplings, in one of the classes I showed this molecule, where I said carbon 13 is labeled. In which case, this molecule, there are three heteronuclear A, M and X. I said it is a weakly coupled AMX spin system, where I explained to you about active coupling and passive couplings. You know that? This, you don't forget that. In the proton spectrum, when I see it is the active spin and fluorine and carbon 13 are passive spins, we get from the spectrum these two couplings, and we don't get that. This we discuss, so I am going quickly. Similarly, in the fluorine NMR, fluorine is active, we get these two are the passive spins, and what we are going to get a JCF and JFH, and we don't get in this spectrum. Similarly, carbon 13 NMR, carbon 13 is active and FH are passive spins. So you get these things from this analysis, but you don't get this. This is what we said. But one important point I kept there, I did not explain. I was waiting for this time. If I do one thing, I carefully expand one of the peaks of this fluorine. Look at all this spectrum, each peak is a very, very well resolved sharp peak. This is sharp peak carbon. Look at the fluorine, there is something here. If you carefully see here, what is that? Let us expand and see. If we expand proton spectrum, you see line width is quite good, 0.3 hertz. That is small value. Okay. Whereas carbon 13 is 0.5 hertz, but it is not a artifact or inhomogeneity. It is there, you see, each peak is behaving like that. So you can't ignore that. You have to understand why. Why is happening? Why fluorine is a triplet? What makes fluorine a triplet from this molecule? Of course, don't tell me there are two bromines, it will become a triplet. Bromine will not couple, and more so it is a quadrupolar spin. So what makes it triplet? In the 1D NMR, we saw which is active spin and which is passive spin. We know what are the types of spectra you are going to get. But still, it is a triplet. And it is a genuine spectrum. Nothing is wrong in that. How do you analyze that? What we do is, the clue is, bromine has two isotopes. 81 and 79. Bromine 81 and bromine 79. And both have spin 3 by 2. Bromine have 81 and 79, both have spin 3 by 2. Interestingly, the natural abundance of both of them are 49.5 and 50.5. So almost 50-50 you can say. Don't worry about 0.5%. Both of them are equally abundant. 50-50. Very interesting. Bromine has two isotopes. Both have spin 3 by 2 and both are equally abundant, more or less. Now, let us look at what are the possible isotopomers we can think of in this molecule. First situation, both the bromine can be 79. It can exist as bromine 79. There's one possibility. There's another possibility. Both the bromines can exist as bromine 81. That's correct. That's also possible. Think of another possibility. This bromine exists in 79. This bromine exists in 81. Is there any possibility? Of course, one more possibility. This bromine can be 81 and this bromine can be 79. And these two are indistinguishable. You cannot distinguish. There are two possibilities here. So how many isotopomers are there in this molecule? 4 different isotopomers. And what is the possible probability of each of them? Because of equal abundance, this is 25%. There are 4 more. If there are 100 molecules, this is 25%. This is 25%. This is 25%. This is 25%. All are equally probable. Right? All are equally probable now. If you carefully see, C and D are indistinguishable. That's what I said. Whether bromine is 79 is here or 79 is here, whether 81 is here or 81 is here, doesn't matter. Because these are indistinguishable isotopomers. So, If you look at the fluorine spectrum, okay. So now before going further, let me complete this. Because of that, what you are seeing is four peaks corresponding to four different isotopomers. Okay, this fluorine spectrum gives one fluorine peak for this, one for this isotopomer, one for this, and one for this isotopomer. But as I said, these two isotopomers have equal probability and they are indistinguishable. These two peaks overlap. As a consequence, in your fluorine spectrum, it appears like a triplet, 1, 2, 1 intensity. But in reality, it is not 1:2:1 intensity. It is 1, 1, 1, 1, 4 isotopomers. Each isotopomer gives a single fluorine peak. Each peak should be a singlet. Okay. But because of isotopomer, it becomes four peaks, four isotopomer. These two being indistinguishable overlap and appear as a triplet. That is the reason why you got a triplet. You understand the logic? How I suppose changing the isotopic substitution, the weight bromines here 81 becomes 17 area molecule. The atomic weight already spectrum is slightly different. See, this is the beauty of NMR. That's what I said in the beginning itself. The beauty of NMR lies is so we can study even microscopic perturbation at the site of the nucleus. So we can understand what is happening at the site of the nucleus just by microscopic change in the electronic charge distribution, and that gets reflected in the spectrum. That's what I wanted to tell how isotopic effect is affecting. Okay, now next I said this already we discussed CFCl3 molecule. I said there are four possible peaks we get for the CFCl3. 100%, 95, 33% intensity. Now, how do I understand this? I explained this to you. There is a possibility all the chlorine could be 35 with 76% abundance. And I worked out and showed you this is the intensity I normalized to 100%. And next possibility is two chlorine they are 35 and one chlorine with 37. Like this and this 35, this and this 35, this and this 35. One is 37. Three such possibilities, and I showed you this is the intensity you are going to get when you compare with the normalized first molecule. Same way we saw for the molecule with two chlorines are 37 and one is 35. This is item I don't want to repeat because it is already talked in one of the classes before. And we also saw the probability for chlorine all 37 and we found out the intensity is 3%. As a consequence, we knew intensity ratios the peaks in CFCl3 are 100, 95, 30 and 1. Remember when we understood a single spin system giving multiple peaks, we discussed this isotopic effect. I didn't say it is isotopic effect explicitly there, but now it is. Of course, I think I mentioned. But in any case, I am explaining to you now. We calculated intensity, everything on that day. We worked out the intensity pattern. We also discussed why we are getting different types of isotopomers. Finally, the intensity pattern is statistical distribution of isotopomers population. And that is what happened. But remember, another interesting point I want to tell you is there is a shift in the peak position as a effect of substitution of different chlorines. So this is all chlorine 35. This is 235, 137. This is 135, 237. This is all 37. So in this case, what is happening? The shift to the high field is for the chlorine, which is 37. Same thing we observed in the earlier also, right? The isotopic substitution, when you think the heavier atom is substituted, it shifts to the high field. That's what we observed in the earlier example also. So this is isotopic effect. Moment to make a substitution or another isotope is present, probability of distribution of populations are there, then you get multiple peaks and you have to carefully analyze them. All right. Now you can work out varieties of patterns like this. Instead of CFCl3, I take what happens if it is CF2Cl2, if it is CF3Cl. You can work out. I gave an example for CFCl3. The same way, if I ask you, I give you a molecule CF2Cl2. Now chlorine, I tell you 76 and 24% of our different isotopes of chlorine. Calculate all the intensity of the isotope peaks, number of peaks that are possible. You can work out. Take the possibility in the CF2, Cl2 first, all are 35. In this case, all are 37. In this case, 137. And so all these things you find out. Can you find out the ratio of the populations? You can get the intensities easily. Now you don't have to worry. What the intensity you get experimentally, you can theoretically calculate simply by looking at population distributions, how statistically they are distributed. Okay. So this is what I wanted to tell you. And see here, same thing in the phosphorus 31 NMR. Very interesting thing happens. Phosphorus, it chlorine. See, always these halogens, fluorine, bromine, chlorine substituent case, wherever it is substituted, this type of isotopic effects are largely seen. We saw that in the first example, in the fluorinated molecule with bromine substitution, then CFCl3, now in PCl3. Generally, this type of isotopic effects and isotopic shifts is dominant in halogen substituted molecules like this. So now in the PCl3 also you can work out all the chlorine can be 35, like similar to CFCl3. Here I am observing the phosphorus NMR. You can calculate all the intensities very nicely, exactly to obey same intensity pattern. Like what is the intensity pattern? What you got for CFCl3, 100, 95, 30, and 3 you will get. Okay, and you can see this effect when you, especially when you have a more complex, like say platinum with the 6 chlorine complex, and you see many peaks you are observing. Actually, in principle, in the platinum NMR, if you see, you must see only single peak, but varieties of isotopes are present here. As a consequence, different peaks you are going to get. In principle, you can calculate what are the possible isotopes. You find out and calculate the peak intensities. Okay, same thing which is platinum bromine. Now I will take another simple example. This is a very nice example. I like it. Look at this spectrum. This is a tin NMR I am doing. Tin NMR spectra of SnH3 minus and its deuterated analogs in liquid ammonia. This is the statement taken from ChemCom. What is tin 119 NMR? Because it is a spin-off nuclei, remember, tin 119, and it is NMR active. Abundance is about 78%, doesn't matter. So now we are looking for the tin 119 NMR. This answer lies in the statement here. Deuterated analogs in liquid ammonia. How many deuterated analogs you can think of? There is one possibility, SnH3 minus, everything is protonated. Or one may be deuterated, SnH2D. Two may be deuterated, SnHD2. Or all the 3 protons can be deuterated, SnD3. So there are 4 different types of isotopes possible because of substitution of deuterium. 4 different types of molecules you can think of. Now we can analyze the spectrum if you understand what are the deuterated analogs there. Are you all with me? Please understand. Now consider the first one, SnH3 minus. When there are 3 equivalent protons are there, what happens to tin NMR? This signal, it will become a quartet, like magnetically 3 equivalent spins, like CH3. You saw in the carbon NMR, right? CH3 carbon will become a quartet because of 3 protons. Exactly, tin will become a quartet. This is exactly corresponding to SnH3 minus. Now we'll take the next one. Next one is SnH2D. What happens now? H2 means like CH2. Then it will split this S10 into a triplet. Because there is one deuterium, what will happen? Each deuterium, each lane of the triplet is split into 3 lanes of equal intensity by deuterium. This is what we understood, when we are understanding CD3C and CD2C and all the spectra we discussed. Even CDCl3, if you look at it, carbon 13, it is split into 3 lines of equal intensity because of deuterium. So exactly, first tin is going to be split into triplet by 2 protons, and one deuterium is makes each of these triplet line into 3 lanes of equal intensity. This is also understood. Then next is this one. What is this? This is a possibility SNH T2. When it is one proton is there, it's like a CH proton. When the carbon is split into a doublet by proton, right? Similarly, theme is going to split into a doublet here by this one proton. But there are D2, two deuteriums are there. Two of the protons are replaced by deuterium. What that will do? That will split each lane of the doublet into 5-lane pattern, which we also worked out the intensity very recently, right? 1, 3, 1, 2, 3 to 1. We got it. What is the last possibility? All the three can be deuterium, right? It is Sn D3 minus. When 3 deuteriums are there, you can find out it splits into 7 lines. We saw that, you put 2Na plus 1. N is equal to 3, I is equal to 1, 3 into 2, 6 plus 1, 7 lines. You should get, and we also calculate the intensity when we are observed CD3CH spectrum, right? So it will get 7 lines, but it is a poor quality spectrum. You are not seeing 7 lines. But what I wanted to tell you is, look at it, isotopic effect. Just by changing one of the hydrogen to its deuteration, change it to deuterium, that drastically you can see the effect on the spectrum, and also peaks. How much it has shifted by 1 deuterium, 2 deuterium, 3 deuterium, and you can in fact find out the difference, chemical shift difference between here to here, and this to this center, and this to this center. In fact, all are equal. It linearly changes. So you can find out if there are 1 deuterium substitution, what is the isotopic shift because of 1 heavy atom substitution. What is isotopic shift when there are 2 heavy atoms or when there are 3 heavy atoms substituted. So all these things can be easily calculated. These are all the effects of isotopes you can see here. Now, I'm going to give you a last example of this, I think, next class. So now look at the fluorine NMR spectrum of vinyl fluoride. This is a vinyl fluoride. When there is single fluorine, proton decoupled, remember. So no proton fluorine coupling, you get a single peak. What about if I have deuterium here? One instead of proton, I replace one of the proton by a deuterium. It becomes 3 lines. Now I put deuterium here. Very interesting because it is a trans coupling. This is a cis coupling. You are going to get this. When the deuterium is here, you get this thing. When the deuterium is here, 2 deuteriums are there, you get this. And 2 deuteriums in the trans position, 2 deuteriums in the geminal position, and 2 deuteriums in the cis position. Fantastic spectrum. You see, so beautifully you can understand the effect of substitution of deuterium, not only isotopic shift, how the spectrum is getting affected, whether it's 1 deuterium is there or 2 deuterium is there, depending on whether it is a geminal, vicinal, trans or cis. Based on that, entire pattern changes. I hope we can understand. Maybe if there is 1 minute, 5 minutes time to next class, 2-3 minutes I'll see and explain this to you, and then afterwards we go to multinuclear analysis. So I'll stop it today.